Okay, so in this case, good morning, good afternoon, good evening, everybody, in whichever time zone you currently are. I'd like to welcome each and every one of you to PODS 2021, those who are present in Xi'an and those who are attending the conference like me virtually. It's a pity that meeting in person is impossible for the international community for the second year in a row, but I'm very grateful to the local organizers for their tremendous effort to set up a hybrid event to allow researchers around the world to join and interact as much as is possible in a virtual setting. I'd also like to extend my thanks to everybody who has collaborated in making this conference happen, despite all the problems the world is currently facing in this seemingly never-ending pandemic. Thank you all who served in the various committees and as conference officers, and above all, thank you to the authors who submitted to PODS. And I'm also grateful to the sponsors, in particular SIGMOD, SIGACT, and SIGAI. PODS is running under the auspices of these three ACM6. It's a tradition of SIGMOD PODS that Monday is the so-called PODS only day. And it's also a tradition that PODS starts with one of the highlights of the conference, namely the keynote. It's my great pleasure to introduce this year's keynote speaker, Rajev Alur from the University of Pennsylvania. Rajev obtained his bachelor's degree from IIT Kanpur and his PhD from Stanford University. He then spent some time at the Computing Science Research Center at Bell Labs before he finally joined UPenn over 20 years ago. He has received a great number of honors and awards. Just to mention a few, he's a fellow of the AAAS, a fellow of the ACM, a fellow of the IEEE, and he has also received the inaugural Alonzo Church Award for outstanding contributions to logic and computation. His research interests span all kinds of aspects of formal methods for system design, and he has published dozens of papers in top venues such as CAF and LIX and STOCK and Fox, ICAL, POPL, you name it. He's the author of a textbook, or the textbook, on principles of cyber physical systems. And he has also had a PODS paper a couple of years ago, actually in 2007 to be precise. So Rajev, it's great to have you back at PODS, and the floor, even though only virtually, is yours. Please.
Thank you very much. Thank you, Reinhard, for that kind introduction. Thank you to the PODS organizing committee to give me this opportunity to speak to PODS. So Reinhard, you actually mentioned that I have a PODS paper, and that year the PODS was in China. It was in Beijing.
Indeed, that's right. Yeah, in 2007.
Pleasure to actually, to travel to PODS, and that was my first trip to China and give the talk in person. Today, unfortunately, I'm giving the talk remotely, but yeah, I'm very grateful to the organizers, to the great hybrid format that they have put together. So today I'm going to talk about some ongoing work on synchronization schemas, which is a way to model data for streaming, distributed stream processing systems. And I'm hoping that this can serve as a foundation, a theoretical foundation for logics and models over streaming data. And this is joint work with a number of faculty and students at Penn, and in particular, the database community will know well my faculty colleagues here, Zach Ives and Val Tannen, who are co-authors on this work. So the context and motivation for this work is real-time decision-making, particularly in the setting of Internet of Things IoT systems. And examples of such systems are plenty: smart buildings, network switches, health monitoring devices. And in all these settings, the data is produced in a distributed fashion, and the system is tasked with process this data, compute some analytics, and make a decision in real time and send some feedback signal to the system in a closed feedback loop. And to do this effectively, we would like predictable latency. Right? So this has actually motivated development of a number of distributed stream processing systems. It's a very active research area, both in academia, but also there are a number of solutions developed in industry, very robust high-performance systems. And according to Google, the top 10 systems, well, according to popularity, turn out to be the ones that I have listed here. So starting from Google Cloud Dataflow to Apache Flink. So these systems focus more on high performance and fault tolerance. Right? So they're highly engineered systems. And if you look at the programming API they provide, it's typically built on top of data flow models. And the user can specify the computation that they want using extensions of SQL. Typically, the streaming extensions of SQL allow you to have windowing constructs. So for example, if the query says that output every minute some statistics of the events that you have seen in past 1 hour, so that's a sliding window construct. And then so every minute you look at the events that have happened in the last 1 hour, and then to think of that as a relation and apply a SQL query. And a lot of work has gone into how do you compute this efficiently as this set of events changes over time, right? Now, if you want to do more complicated forms of computations, then these systems provide user-defined functions. And typically the direct support for parallelization that's provided, it's for fixed patterns such as partitioning the data based on certain keys or computing some relational aggregates. If the query involves more complicated forms of synchronization and computation, then the programmability is not that great. So to illustrate this, let me use this example, and I'm going to use this example throughout this talk. And this is a system where maybe a transportation system is monitoring data collected by the fleet of taxis it runs. And there are two types of events: the GPS events that carry some information about the location of different taxis, and ride completed events, so denoted by triangles here. They carry information about, say, the fares that the customers pay at the end of a ride, right? And in my talk, I'm going to use different colors to illustrate different taxis. So in this picture, you see a yellow taxi and a purple taxi, right? So let's think of a computation. So well, in the first phase, what we want to do is that every hour for every taxi, we want to compute the revenue. Well, the revenue depends on the distance traveled, which can be computed based on the data that the GPS events for that taxi carry. But one thing to note here is that to compute the distance, the temporal ordering of these GPS events, which may carry some timestamps, so that temporal ordering is crucial. On the other hand, the fare, total fare collected by a taxi could depend only on the ride completed events. And there you could think of it as a bag and just apply a standard relational aggregation, right? So you have like mixed ordering in terms of what's actually required from the perspective of the query processor. And suppose we want to compute the total revenue in each hour and mark certain hours as peak hours. So the peak hours could be the ones where say the revenue is much higher compared to the adjacent Rs, right? So this is an example of a time series dependent computation. And in the context of, say, monitoring of health data, these time series based computations are crucial, where you want to do operations like smoothing or detect peaks and surges. And typically the relational query languages do not provide a good support, a high level API to express such time series dependent computations. And now suppose in HR, based on the revenue, we also want to compute which taxis contribute a lot more significantly relative to other taxis, and let's call these star taxis. So the exact definition doesn't matter, but based on the revenues of taxis, we want to mark certain taxis as the high performing ones. And this is a traditional relational computation, and that can be expressed in some complex form of filter and can be expressed in typical relational languages like SQL. And finally, having marked certain Rs as peak Rs and having marked certain taxis as star taxis in HR, we want to output which taxis are star taxis in successive peak Rs. So this is a kind of a temporal join. So every peak R, you want to join the set of star taxis in that R with star taxis in the most recent peak R. So this is, you have to look back in time. And so this is an example of a more, what people would call like complex event processing kind of a query, right? So when you have a mixture of such computations, then the existing APIs for distributed stream processing systems do not offer good solutions, right? So the user is faced with three unattractive choices. One is, since these systems allow you to do low-level programming, you could just program the most efficient way of programming the query that I just described at a low level. But this is kind of error-prone manual programming. The other option is you use, so for example, if you're using Flink, you could set it up as a data flow graph, and allow the system to do parallelization. But since here, say the temporal ordering of the GPS events was crucial, so this aggressive parallelization could lead to non-deterministic or incorrect outputs, right? So you lose correctness. The third alternative is you just program the system as if it's a sequential computation. So you set the parallelization level to 1, but in which case you pay the performance penalty. And automatically parallelizing sequential code is a hard task. And actually, so the lack of good programming APIs in this context, when you have a mix of sequential and relational computation, is also reflected, or maybe it's caused by the fact that if you look at the typical theory work in the PODS community, that's focused more on algorithms for streaming, so how to compute say certain specific function over streaming data with as little memory as possible. But if you think about models and logics, even though we have a rich history and wonderful literature on relational models and sequential models, when we have this mix, there are very little research on that. And so this work is actually one proposal, and it's our solution as a new data model for modeling streaming data. And the view is based in viewing data as a partially ordered model. And in fact, what I'm going to talk about specifically are called partially ordered multisets, or called POM sets. So I will begin with introduction to POM sets and why we should be looking at POM set in the context of processing streams. Then I'll tell you about a particular class of POM sets, which are structured POM sets, and they are like series parallel graphs. And we are going to define them using what we call synchronization schemas, and that's the title of my talk. So synchronization schemas are types for modeling streaming data, and series parallel streams are objects of these types. Then I'll tell you about series parallel stream transformers. So just like tree transformations or graph transformations, this is a language for transforming series parallel streams, and that can provide a foundation for writing queries for in this context. So I'll give you some examples of queries, and then I will end with an invitation for future research. So this is ongoing work, and I'm looking forward to have a dialogue, particularly with the PODS researchers on how we can build some logics and models using this foundation. So let me start by first telling you about POM sets, or partially ordered multisets, and the motivation for them in the context of streaming data. So if you think of a stream, so maybe the first thought is that a stream is a linearly ordered sequence of items, right? So your inputs, if the tuple in the input stream is of, say, some type A, then the input stream can be modeled as a finite sequence over A items. So it's an element of A star. And if the output tuples are of type B, then the output stream, it belongs to the set B star. And then a stream transformation is just a function from A star to B star. In the streaming context, we would like this function to be monotonic with respect to the prefix ordering. So if I extend the input stream using the prefix ordering, the output stream should only extend. So that allows incremental computation, and monotonicity with respect to prefix ordering is key in the context of streaming. Right? And this has a very clean mathematical formalization, and a number of proposals in database community and also in programming languages in what people call reactive programming. They're based on this, but this is kind of restrictive, and it's restrictive in two ways. One is if the query itself is relational. So for example, in our sample query, at some point I wanted to compute the total fare, where that could have been parallelized, and it's a relational operation. So that if in the purely sequential view, this kind of relational queries, the parallelization that they allow, and the rich theory of optimizing relational queries cannot be directly applied. Right? From the perspective of data generation, we know that in a distributed system, not all events are causally related. And if we want to enforce a consistent or temporal ordering across all events in a distributed system, well, there are protocols for that, but the synchronization overhead for that has a performance penalty, and when it's not needed, we should try to avoid paying that penalty. Right? So at the other extreme, we may think of the stream more as a relation, but of course here, as time goes by, more and more items are being added to this relation, so it's kind of a relation that gets incrementally updated. One challenge with a purely relational view is that if our query says that every minute output something that happened in, say, last 1 hour, so we would like so if our view is only relational, then without these synchronization markers, we cannot forget events, and the state would keep growing unboundedly. And so this was actually observed even in the early days of work on streaming data. And one really nice piece of work is this system called, the language called CQL, Continuous Query Language, by Widom's group at Stanford. And they have a clean formalization there of streaming data as a sequence of relations. And that led to a lot of research, and people came up with different ideas of these punctuation markers. So this the markers at which you flush the state and produce an output doesn't have to be based on timestamps. It could be based on events. And those could be modeled using these, what are called punctuation markers. And an example of such work is by Meyer. He has a series of papers on this topic with different co-authors. So that's a nice view. But if we want a stream to be partitioned by key values, then what you really get is a set of streams. And if we are thinking of the model as sequence of relations, then we can't even talk about it. And that's why in a lot of this literature, the expressiveness is kind of limited. So the windowing is allowed, but some nested windows are not allowed. So to motivate the partially ordered view, let's go back to the streaming computation I was talking about. So we have GPS events and we have write completed events. And at the beginning, what we wanted to do was compute the revenue for each taxi every hour. And it involved using GPS events. We wanted to compute total distance traveled by each taxi. And using write completed events, we wanted to compute the total fare charged by each taxi. And the ordering and synchronization constraints implied by this computation then can be captured by this partially ordered structure that you now see on this slide. So since we wanted to output something at the end of each hour, we have to introduce these special events, also called synchronization markers in the streaming literature, and they're depicted as stars. So these are end of hour synchronization events. And so you can think of the data stream as punctuated by this end of hour events. And in between, instead of saying that I have a relation, now I have a more interesting structure, and which is really partially ordered. And the ordering constraints, which are denoted by these, by the edges here. So you can think of this as a labeled graph, where the vertices are labeled with data items, and edges correspond to the desired causal order or the desired temporal order between the between different events. So what this is saying is that GPS events belonging to the yellow taxi are totally ordered. GPS events belonging to the purple taxi are also ordered, but GPS events across different taxis are not ordered, right? So that's because we, so this corresponds to partitioning the GPS events by the key of taxi ID. And then the write completed events are also completely unordered, right? So this is the desired logical view of data, right? Which just says that GPS events of the same taxi are linearly ordered, and all events are ordered with respect to the end of hour, because we want to know which events belong to which hour, right? And this now can be viewed as a contract between the data generation and the query processing, right? And so actually at this point, we can abstract away from the specific computation that I wanted to do and just focus on the ordering constraint. And it's nicely reflected by this shape or by this partial order here. And what it's saying is that for items that are ordered, the implementation must introduce enough synchronization so that they arrive. The ordering information is reflected in the way the events are generated. So if they actually happened at different nodes in the distributed system, then synchronization overhead must be paid so that they get consistently ordered. But such overhead doesn't have to be paid for unordered items. From the query processor, the contract is that if some items are unordered, so for example, the write completed events are unordered with respect to each other, then the result of the computation should not depend on the exact order in which these events are received. And in fact, the computation over these events can be parallelized. And so that's reflected in this contract. So then what's this object, right? So it's a partially ordered multiset. So if you think of this as a graph labeled with data items, then different vertices can be labeled with the same item, just like in the standard abstraction of a bag. Same item may appear multiple times, so it's the same idea here. But except now there is this some ordering, but it's not total ordering. It's only partial ordering, and that's why the structure is called partially ordered multiset. It was first studied by Pratt in the 80s, and this was in the context of what people call true models for true concurrency. So if I'm observing the events happening in a distributed system, then certain events are ordered and certain events are not. So instead of modeling them as a set of all possible interleavings, which leads to non-determinism and lot of challenges, if we just were to model it as this partially ordered object, we would be able to reflect the causality and concurrency more accurately. That was the motivation, and was also studied by researchers like Mazurkiewicz in terms of analyzing concurrent systems, right? What we are interested in this as using a model for data and thinking of queries or transformations as mappings from POM sets to POM sets, which hasn't been done in the literature. Observe that sequences are special case where everything is ordered. Bag is a special case where nothing is ordered. Sequences partitioned by keys, so indexed streams, that's a special case. Sequence of relations, nested windows, and so on. So these are all special cases. And what that means that we can build on the existing work on relational and sequential transformations when we start thinking about these transformations. So, so what are the challenges in computing with POM sets? So the POM sets by themselves are highly unstructured. And in general, there is no good theory of computations over partially ordered sets. So what we want to do is to put some order so that it helps us to specify desired ordering constraints, and it helps us to structure the transformations so that the transformations will specify only monotonic functions. And here, by monotonic, what I mean is transformations which map if the input POM set is extended, and so for that we need a notion of prefix ordering. The output POM set will also be extended, just like what we had in the case of modeling streams as linear sequences. So that brings me to this idea of synchronization schemas, which is the going to be a particular way of specifying these partially ordered streams. But this may be a good time to take a short pause and see if anyone has questions regarding this basic idea of modeling streaming data as a partially ordered structure. Okay, so yeah, maybe not. So yeah, but yeah, feel free to ask a question in the chat box, and then yeah, Reinhard can interrupt me if needed. But I'll also pause from time to time to let people ask questions. Yeah. So now comes actually the core idea in our talk, which is to specify partially ordered streams using these types. So these synchronization schemas are just like types. So actually my background is in programming languages and formal methods. And the types have proved to be very useful in programming all kinds of systems. And here we are going to introduce a particular kinds of types for specifying partially ordered data. So these synchronization schemas build on relational schemas. Now, relational schemas, intuitively, we all understand they specify structure of data with integrity constraints. For the context of this talk, we don't need to think about integrity constraints. And this, the exact terminology I'm going to use could be slightly different from what some of you are used to. So let me just clarify it. So using an example. So in our example, the data consisted of three types. So there was an end of R relation where the two fields were, say, maybe date and R. There was a GPS relation, and tuples of that type maybe carried location and taxi ID. And then there was a write completed kinds of tuples, which again will have a list of fields with their types. So I'm going to call these names of relations like end of R, GPS, write completed as headers. Okay, so these are names of relations. Then fields like taxi ID, so we'll call them keys. And then tuples are a tuple. So for example, a write completed tuple will carry a value for taxi ID, a value for the field write ID, and a value for the field cost. So our the data generated in the implementation and the data that's streaming is going to be a tuple of one of these types. And the kinds of data will be specified by listing all the headers, and for each header the corresponding fields and their types. So so relational schema kind of specifies a format for data, right? And we want to extend it with a synchronization schema, which refers to these header names and allows us to express temporal ordering constraints. So for example, we may want to say that the write completed events are independent of the GPS events. So this type of constraint would be expressed using the synchronization schema. And the schema is going to be, formally, it's going to be a type that captures the shape of partially ordered streams. So the series parallel streams that I'll define will be the objects of this type. So the short definition of a schema is that a schema could be a bag of headers, it could be a sequence of headers, it could be a parallel composition of two schemas, it could be a partition by schema using some key fields, and it could be a synchronized schema. So I'm going to go through these, so that's the entire definition, but I'm going to explain these different clauses one by one, so that, because this is the main definition of the talk. So, so let's start with the base schema. So a base schema could be a bag of headers, and this is like saying that it specifies objects which are bags of that type. So for example, if my schema is bag of write completed, then the corresponding stream is just a collection of write completed tuples. Right? So this is so the standard relational view is a special case. At the other extreme, we could say everything is linearly ordered. So if I say the schema is sequence of GPS, then it specifies totally ordered sequence of GPS tuples. So sequence of H means a linearly ordered sequence of tuples of type H, where H is a set of headers, right? It turns out that this particular schema is definable using other schemas, but it's good to think of it as a special case, a base case. So now we have three ways of combining schemas to form more complex schemas, and the corresponding objects would be series parallel streams of more complex shapes, right? So we had bags and sequences, and how do we form more complex types of partially ordered objects? So one clause is that if K is a set of fields or keys and S is a schema, then partition by K comma S specifies a set of parallel streams, each of type S, and it's indexed by values for keys in K. So this is, so I think key-based partitioning is very common in database literature. So for example, in map, the MapReduce uses something like this. So the only difference, this is a more general thing, where when we partition by K, what we actually get is objects that have more complex form, which are inductively defined, right? But going back to our example, if I were to say my schema is partitioned by the field taxi ID, and the base schema is sequence of GPS, then this is just specifying a set of GPS sequences of GPS events, where each event corresponds to a particular taxi ID field. So there is a sequence of yellow GPS events, and there is a sequence of purple GPS events. So this raises this question that what's the type of the sequence of yellow GPS events? Well, it is a sequence of GPS events, but it has an additional characteristic, namely that the taxi ID field for all these events is yellow. So in the type terminology, this would be a refinement type of the type sequence of GPS. So it's specific type, it's sequence of GPS with taxi ID equal to yellow. So in this type theoretic world, we are going to have actually many, we can build on many nice type theoretic ideas, such as refinement types and higher order types and subtypes and so on. The next way of building complex stream is by parallel composition. So in this example, so I have one stream which is of type bag of write completed, and another stream which is a sequence of GPS events partitioned by the taxi ID field. I can compose these two in parallel by applying the, well, syntactically we are calling it par, but it's just basic. If you think of the corresponding objects, you take two series parallel streams, and when you parallelly compose them, there are no cross-cutting edges, right? So this is just like a parallel graph, right? Or in the terminology of trees, these would be like ordered siblings, right? So when we apply this schema, the names of headers that appear in S and those that appear in S prime, that have to be disjoint. And this disjointness is going to be crucial in computation and in, or if I give you a linear sequence of events, how do I parse it into this partially ordered structure? So that it will turn out that we can do this parsing uniquely because of these requirements that the schema tells you exactly which component that it goes to, and that's determined by the name of the header, and the headers in the two paths are disjoint. And the final clause in building complex stream is what we call sync of H comma S. So if H is, it specifies certain headers, names of headers. So for example, end of R, and S is a schema that you have already defined. Then what this schema specifies is a stream, which is a linear sequence of events of type H. So these are like synchronization markers. So could be, say, end of R events. And in between these end of R events, you have objects of type S. So which would be substreams of type S, right? So it's a linear sequence of events of type H interspersed with streams of type S, right? In other words, the events in H act as synchronization markers for events in S. And in our example, we can then build the desired structure by saying that it's a end of R is synchronization for streams which are parallel composition of a bag of write completed events and a sequence of GPS events partitioned by taxi ID. So this was actually the partially ordered structure that we started with, but now it's specified inductively using these constructs, right? So just to recap, a schema is a type that captures the shape of partially ordered streams. Its inductive definition has base case of bags and then three ways of building complex streams: parallel composition, key-based partitioning, and synchronization. And series parallel streams are the inductively defined objects, and their definitions are nice and clean. And they are general enough to what we want to model in this streaming world, like sequences, bags, and so on. It should be noted that not all partially ordered structures can be captured using these schemas, right? So what are these schemas doing? Well, they are imposing a nice inductive structure so that you can do structural induction to define computation. And one of the requirements, for example, would be that if certain events are declared to be unordered by the schema, then your computation should not depend on the order in which they get processed, right? So this is crucial. And in general, to enforce that using static or even dynamic requirements, it's challenging. But since we are looking at streams that are defined in this inductive way, we will be able to get that result. We will be able to define the computation that reflects the structure of the input stream, so that the result of the computation will never depend on the order in which unordered events get processed, right? So that's why this definition turns out to be crucial to the results that we get. It's actually obvious how to define a prefix over the series parallel stream. So what you see on the right is the stream that we were looking at. So if I take a vertical cut through this, which the intuitive notion of a cut, then what you get is an example of a cut would lead to the structure that you see on the left. And we can then say that the object on the left is a prefix of the partially ordered structure on the right. Similarly, we can define operations like concatenations and suffixes and many typical mathematical operations over sequences generalize nicely to these series parallel graphs. One nice thing about our definition is that if I gave you a linearization of the partial order, I think it's easy to understand it visually. So on the left, what you see is a way of a flattening or a linearization of all the events that appear in the partially ordered structure on the right. So they have exactly the same number of, say, yellow GPS events and the yellow write completed events. And it's consistent with the partial order on the right. So such a thing is called a linearization of a partial order. What we can show is that if I gave you a linearization and if we knew the schema, then we can reconstruct the partial order, the series parallel stream on the right uniquely, right? So, and that's because the series parallel stream actually tells you how to, if, for example, if something is a parallel composition of two graphs, the type tells you which events go to which part of the graph, right? And this is crucial in ensuring that the computation does not depend on the order in which the spurious order in which you may receive the data. Right? It depends only on the causal ordering that's inherent in the partially ordered structure. And one final thing I want to talk about the schemas is this idea of subtypes or relaxation. So in type, subtypes play a crucial role. So here, let's just think about the ordering constraints. So a synchronization schema imposes certain kinds of ordering constraints over different events. So for example, the GPS events of the same taxi were ordered. So if I drop that constraint, what we get is a relaxed schema. And again, it's easier to visualize this and understand it using an example. So here is the schema that we were looking at. So the sync of end of R and ... So that's actually the type. But an example of a partially ordered structure of that type is the one that we have been looking at in the talk. And if I say that, between the end of R events, even the ordering of the GPS events of the same taxi is not important, then the resulting structure that I would get is well, you have end of R events, and in between you have a bag of GPS and write completed events. Right? So as you can see, it's really the same graph with the same number of vertices, and some edges have been dropped. And this is exactly subtyping in the context of the schema. So at the bottom, you see the schema is sync of end of R and bag of GPS write completed. Right? So that's the type, that's the schema. And then you may want to ask is that if I give you these two schemas, the one on the top and the one on the bottom, can we check if one schema is a relaxation of the other one? So this is the problem of type checking. It's given two types, is one a subtype of the other. And it turns out that in this particular context, that can be checked actually quite efficiently. And there is a polynomial time algorithm for doing this. So that brings me to the next part of the talk, which is thinking about how to write transformers over these series parallel streams. But again, let me take a pause for a minute and see if anyone has any question about the synchronization schemas and the series parallel streams.
Maybe Rajiv, may I ask you a question? Because on one slide you mentioned that not all POM sets are captured by this formalism.
Yeah.
Can you give us an idea what you left out and why it doesn't do no harm? Why it's why this is, say, a good decision to leave out these remaining POM sets?
Yeah, very good question. So an example is if you look at, say, a square with, let's say, so if you have if you have 4 types, A, B, C, D, and if the partial ordering is a square whose vertices are labeled with A, B, C, D. So like A is dependent on B and D, B is dependent on A and C, and so on, right? And so this actually cannot be specified. It's not a series. You cannot decompose it into a series parallel graph, basically, and as a result, you cannot specify it as using the series using synchronization schemas. The reason, so I think the definition that we have, it generalizes all the queries and examples we have seen in the literature. Of course, that's not evidence that we haven't left out interesting computations, but the benefit is that the transformations over the series parallel streams now can be defined inductively, and for general partial orders, that's challenging. I think there is no nice inductive definition. It has to be very global. You have to basically carry on the frontier of the partial order at every step, and that leads to quite a messy definition. So it's a trade-off between kind of mathematical elegance and generality, but it's I guess open to debate. I mean, maybe there could be generalizations.
Thank you very much. Yeah, makes perfect sense. Thank you.
Okay, so now let's talk about the stream transformations, right? So what is it that we want to specify, right? So what should be a transformer? Well, we know about relational transformers, right? So in this beautiful theory of relational transformers, there is also a beautiful theory of sequential transformers. And here what we want is take this partially ordered structures and output a partially ordered structure. Here is just one illustration. And the type of the input stream will be specified by some schema S, and then the type of the output stream will be specified using another schema.
Excuse me, Rajev, sorry for interrupting you. There is someone on site has raised the hand, so maybe we should give the person who has raised the hand the chance to ask the question. Yeah?
Yeah.
Please go ahead. Someone on site. I just see on the panel someone on site raised the hand. No? Then
hello, I'm here in Shan. Yeah, so
please,
I
have
a question about the parallel composition. You said that the schema has to be disjoint, but I'm thinking about the sliding window. Sometimes they kind of have overlapping. So can you explain a little bit about the disjoint and the overlapping in the sliding window?
Oh, that's a great question. So so in the sliding window, actually, it's going to be a more complex form of joint. So actually, that's not going to be parallel, but the events that you select within the sliding window, I think that they could have, they themselves could have a parallel within it. But you are right. So I think if you look at 2 sliding windows, then they cannot be processed in parallel because they have common events. Right? Yeah. So the sliding window is a special kind of stream transformer which can be defined using the operators we have shown, but the structure is more complicated, and it's not. Yeah. So there is no simple parallelism there. Yeah. Okay, so what we now want to define, yeah, I hope this answered your question. So, but yeah, let me continue with the transformations, which, so the goal of defining this transformation language is to have an intermediate representation between user queries and an implementation which can do query optimization from these transformations, right? And these transformers could be useful in understanding expressiveness and asking questions like what's the query evaluation complexity. So for example, for the sliding window queries that were just asked, right? Yeah. So I'm going to illustrate some aspects of this definition. So this, these definitions are somewhat complicated, but I want to give you some highlights of the definition, and then the details are in the paper. So the precise definition of the transformer takes an input stream and produces an output stream, and there is a type, a schema for the input stream and a schema for the output stream. But it also takes an initial value and returns a final value, and we will see why those are useful, so particularly in aggregates. And the formal semantics of these objects is going to be defined as a deterministic function. And these transformations are going to be defined inductively by referring to the structure of the input schema. So the base schema was an example base schema was bag of H, where this would just be a relational transformer, and this could be written in any language that you want. It has to be monotonic in output, so if you add more things to the input bag, then what you produce has to only grow, and that's important in the streaming setting. The final value could be used to compute relational aggregates. So if this transformer is being called by some higher level transformer, then it can return the aggregate. Right? So let's think about parallelism. And so if the input schema says it's parallel of S1 and S2, then the input stream consists of two disconnected graphs, I1 of type S1 and I2 of type S2. And what do we want? We want that this transformer should exploit this parallelism. In fact, and that will also ensure that the events that are declared to be parallel so this is like a contract, right? So the schema is saying that these events should be viewed as parallel. Their order it's not important to the computation. Well, then the computation should actually make sure that they're processed in parallel, right? And also, if I had defined a transformer T1, which processes inputs of type S1, and if I had defined a transformer T2 that processes inputs of type S2, and the S1 and S2 themselves could be more complicated types, they could have interesting series parallel structure within them, I should be able to reuse them. So approximately then this transformer is just going to look like running a transformer T1 in parallel with transformer T2. When this composite transformer gets an initial value, it can pass it to both the transformers T1 and T2, and when it returns, it could take the return values of T1 and T2 and return the final value. So there are some interesting technical aspects which I'm hiding, and you can see them in the proceedings. So here the output of what I just defined, the output is also a parallel composition of two graphs. What if the two things have things in common, right? And well, should this be allowed or not? So it turns out that it can be allowed with certain restrictions, which can be checked, right? But more generally, if you think of a graph transformation, which is mapping inputs with shape S to outputs of shape S prime, does the shape S prime have to be isomorphic to the shape S? Well, it doesn't have to be, and there has to be some kind of bisimulation relation between the two, and that's explained in the paper, right? The case of key-based partitioning is, it's analogous, but is more complicated because you do a reduce when these transformers corresponding to each value of the key return, and can be viewed as a generalization of the more traditional map reduce, right? But let me illustrate one aspect related to defining formal semantics using the case of hierarchical SPSTs, or when the input stream has type H are the synchronization markers, and the in between H, we have substreams of this type S prime. So the input stream looks like, you have a tuple H1 of type H, then you have a stream I1 of type S prime, which is a complicated series parallel stream, and then there is a synchronization marker H2 and so on, right? So if we have defined it a transformer T prime which handles streams of S prime, how would we define a transformer T which handles streams of this more complex type? Well, it should keep its own state, which gets updated while processing H tuples. And every time it's, the substream S prime starts, it can call T prime, right? So one challenge that shows up is, so imagine in this picture, at some point you are processing events in S prime, right? So at this time, T prime is running, right? What should be the semantics of T prime? Well, given a stream of type S prime, it should return, it should map it to some output stream of a particular type, right? But how its computation proceeds depends on what the next item is. If the next item is a synchronization marker in H, then this transformer has to return. And whenever a transformer returns, it has to do some extra computation. So like, for example, in MapReduce, if there is we want to do the reduction, then in fact there could be a lot of computation and a lot of output tuples could be generated, right? But if the next tuple is of type S prime, then there is no return and the computation continues. And this actually issue shows up in many, has shown up in the streaming literature earlier. So what happens, how do you deal with end of stream marker, or how do you deal with punctuation marks? And I think we have a clean solution here. So we define two types of semantics: an open semantics, which assumes that the stream, will continue to process the current stream. So the next item will belong to the current stream. And the closed semantics, it assumes that the transformer is returning. And this closed semantics will return a final value also, right? So yeah, I did not get into the details of that, but I would like to just summarize the features of these SPSTs. So firstly, it has a deterministic semantics, so it's functions over series parallel streams. So a lot of this confusion that happens because of non-deterministic ordering of events goes away. It allows you safe and flexible parallelization, so it's provably correct. So things that are unordered can be processed in parallel without affecting the result of the computation. And it's flexible in the sense that it allows more complex patterns than the more traditional relational aggregation and key-based partitioning. It's streamable, so more specifically, the open semantics, which maps an initial value and an input stream to an output stream, is if the input stream is extended by the prefix ordering, then the output stream also gets extended by the prefix ordering, right? So it's provably monotonic, and it's modular. So if an input schema consists of, will have subschemas, if you have defined transformers processing inputs of those subs corresponding to those subschemas, then those could be reused. The semantics is also reusable. So, so I don't have to look inside T prime. So if the transformer T is using another transformer T prime, then the semantics of T can be defined just using semantics of T prime. And finally, these are composable. You can define a complex computation as a sequence of queries or sequence of SPSTs, and if T is being pipelined with T prime, then the input type of T prime should be a relaxation of the output type of T. So whatever T produces, that can be consumed by T prime. So let me give you a little idea in next 10 minutes, and then I'll wrap up about how can we define query languages over these streams. But yeah, this also may be a good time to take a short pause and see if anyone has a question. Okay, so yeah, let me continue. So so when we want to deploy this,
sorry, Rajesh, for interrupting you.
Yeah.
With some latency, there is a raised hand on site. So please ask the question on site.
Hello, I have a question to ask about the transformer in real distributed streaming systems. Some operation or transformer are stateful. So how this synchronization schema can solve the stateful operator or transformer?
Yeah, no, thank you for that question. No, they are stateful actually. So I think I did not give the complete definitions, but for example, here the when I was talking about this, so this, let's say for this hierarchical case, the transformer does keep a state, and so every time you get the synchronization marker, that state gets updated, right? Yeah. Or even the relational transformer could be, could be stateful. Yeah. So they are stateful transformers. Yeah. So, and the, in fact, these queries that we will see actually, so maybe, I should show you a few queries. So, and they will illustrate that, you can do stateful computation. Yeah. Yeah, but thanks. Yeah.
Thank you.
So, so what we would like is, so the user, so these SPSTs is more like a low-level model, which could be useful for understanding expressiveness and evaluation complexity. But the high-level operators you want, similar to join and.
So sorry, Rajesh. It seems as if the hand has been raised again on site.
Sure. Yeah.
Is there another question on site?
Yes, here's another one. Sorry to interrupt.
No,
Yes,
no, please go ahead. I mean, that's, I think the more interactive our session is, the better, I would say.
Yeah, that's great. So I have a question about the streamability. I think it's a great feature of this theory. So can you share a little bit more about this streamability, especially in the case that given a computation, it could be a traditional aggregation function or some user-defined functions. How do we decide if it can be incrementally computed? Thank you.
Yes, yeah, no, a good question. So the, yeah, I have a feeling that maybe, I think this kind of logical definition of streamability was a bit, may have been misinterpreted. So what this is saying is that anything that you write in this language has this property that if you extend the input, then you would, the output will only be extended. And that's kind of a theorem and the way the computation is structured. If I'm not mistaken, I think you were referring to more like which functions can have like a good streaming implementation, which is more to do with how much state you would have to maintain, right? And in some cases, maybe that state, grows more in an unbounded fashion. In some cases, you can maintain actually a very small amount of state. And that's kind of orthogonal. So, and that's, I think, more related to which functions can be computed efficiently in a streaming fashion. And so what our framework will let you do is it will enforce a typing discipline such that it will be easier to express that streaming computation. But exactly which state to maintain and how to update it will have to depend. If it's a complex streaming computation, then it will have to depend on that, right? Yeah. But the types will make sure that by mistake you don't, the output tuples, when you produce the output tuples, that will keep, growing in a monotonic fashion.
I see. Thank you.
Yeah. Does that answer your question? Yeah. Okay, so we would like take this computation and map it to the a pipeline of SPSTs, and then generate a distributed implementation. So this is kind of work in progress. So the question is, what are good queries over a series parallel graphs, right? Yeah. So we know what are good queries over, say, relational data, and there is beautiful theory of going back to relational algebra about that, right? So we have looking at what kinds of queries people write in streaming computation, and looking at the theory of in the relational setting and sequential setting, we have defined a number of queries like filter, map, different forms of windowing constructs and different kinds of aggregations and joins and map reduce. But let's just go back to the query that we had looked at and see how it would be expressed in our setting, right? So just to remind you, the query that I started with had 4 stages. So the first stage was for each taxi, compute the revenue in each hour, then mark certain hours as peak hours, and that was kind of time series dependent computation. Then in each hour we wanted to tax certain taxis as star taxis because they were high performing, and then finally we wanted to output taxis that are stars in successive peak hours, right? So what's the first step? Well, so this is the shape of the input stream, and that this shape is says which parts could be parallelized and which cannot be parallelized, right? And so we are going to view logically the data in this manner. And in the first phase, what we could do is compute for each taxi total distance traveled each hour using GPS events. So this is sequential aggregation, and this will be applied to the in say the yellow GPS events and the purple GPS events. And this would be a stateful computation, and you can just write your standard sequential iterator, like a list iterator, to do that. Then for each taxi, we can compute the total fare in each hour, and this is a relational aggregation. And this, you can write this in a SQL or any using any relational aggregation. And once you know the distance and the fare, you can compute the revenue. And then the output stream of this phase then could be a sequence where you have these end of markers still are synchronization events. And in between, for every taxi, you have just one revenue tuple. So because this, you have processed the GPS and write completed tuples and mapped them to these revenue tuples, right? So now I'm actually showing multiple revenue tuples. Suppose there are multiple taxis, and to detect peak hours, then what we could do is, well, first annotate each end of our tuple with total revenue. So this is just again relational aggregation, but you add it to the synchronization markers. So say the first hour has revenue 234, the second hour has revenue 538, and so on. And now I want to mark which hours are peak hours. And for simplicity, let's assume 538 is peak because its previous and next hours have lower revenue, right? So that's the definition for this query. So 538 is peak and 1005 is peak, but 420 wasn't peak, right? And how can we do this? Well, we can just add a field. So this is again a stream transformation. So I have an input stream and I produce this output stream where each end of our tuple has an additional bit which says, is it a peak hour or not, right? But to do this, so as you read the end of our tuple for 538, you cannot decide whether it's a peak hour or not, because you have to wait to see the revenue tuples for the next hour. And then only when you see that the revenue of the next hour is 420, you get to decide that 538 is a peak hour. So you need to store the revenue tuples of the subsequent bag, right? And so going back to this question about streamability. So I mean here there is this overhead because it's a time series dependent computation, and you have to remember all the revenue tuples of the next hour before you can actually output 538, right? So the delayed output means that more state needs to be remembered, right? But that's inherent in the computation. And then suppose in each hour, we wanted to compute which taxis have high revenues, or which taxis are star taxis. And this could be based on maybe a taxi whose revenue is one standard deviation away from the average is maybe a star taxi. So this is but a standard filter computation. You can do your favorite relational language to do this, and maybe based on that, maybe in the first hour the purple and the orange taxis are star taxis. And then now for this stream, now we can do an interesting temporal drawing. So in the hour 1005, which is a peak hour, we want to look at the current star taxis from the previous hour and look back in time to the past peak hour, which is 5:38. Look at the star taxis in that hour and take a join, right? And you want to do this in a streaming fashion. So, but this is a self-join. So first question is, how do you specify this? And one nice way of specifying this is by using regular expressions. So we want to find a sequence of these end of hour tuples where which matches some regular pattern. In this case, it's going to be red, blue, star, red. That's going to be the interval. So this is like an event-based window. And this is the precise definition using regular expressions. And since I'm running a bit behind, so I'm going to skip this explanation. But what I want to mention is that the specific temporal join operator we have defined says that if you are evaluating this in a streaming fashion, you need to remember as many banks as linearly proportional to the size of the regular expression, right? Yeah. So the streaming complexity, some people could see this as high, but it's specific. Once you start thinking about logics and so on, you could say that if for queries that are expressible in this logic, you can give precise bounds on what's the amount of information that needs to be remembered in a streaming fashion to evaluate this. And actually, I think this logical view is a bit different. I mean, the challenges and the theorems are a bit different from the more traditional literature on streaming computation, where you're looking at specific computations and asking the question to evaluate this, how much memory do I need, right? Here, these bounds are more general about classes of queries, right? So to summarize this part then, so some complex transformations that involve both relational and time series operations can be specified in a clean fashion. You can get some evaluation bounds. You can specify them as composition of queries. The queries can be nested. They can be applied to substreams. So actually, many of these streaming extensions of SQL, if you have some windowing construct, then what the windowing construct selects is not of the same type as the original stream that you started with. And that's why you can't apply nested windows, or you can't mix time-based windows with event-based windows. Here we have a uniform type system, and that's the key to compositionality and modularity, right? And each query gets translated to this series SPS transformer, and so you get this guarantees of safe parallelization. So let me wrap up in next 5 minutes, and then we can have more discussion by telling you about some of the interesting future directions. So as I said at the beginning, I view this more as an invitation to future research, because I think a number of folks in the PODS community have actually a lot of expertise, both in streaming computation and also in logics and models for different kinds of data models. So their insights would be very useful to build this theory of series parallel streams. So the first thing that we want to do is really demonstrate that this idea is useful in practice. So as I mentioned, there are a number of commercial, high performance stream processing systems out there. So we want to show there is some benefit. And so starting with a pipeline of SPSTs, we want to generate an optimized distributed implementation. And this framework actually allows you to start thinking about how to distribute state. So for example, the GPS events of different taxis are originating maybe at different taxis, and you want to push the computation to the taxis themselves so that only summaries can be exchanged, right? And we have already started doing some work, and there is a paper in PLDI which uses these data trace types, which is actually the earlier incarnation of the synchronization schemas, to show that for certain kinds of queries we get much better performance compared to say Flink or Spark. We also have a paper under submission on how to distribute state efficiently. Another theme for future research is theoretical foundations. So if you look at this partially ordered structure, well, there are bags, there are sequences or strings, there are binary trees. There are also unordered, unbounded trees indexed by key values, also data. So, in the PODS community, there is a lot of work on logics and transducers and automata, which helps us understand expressiveness for these cases like say trees and sequences, right? So can we develop similar theory for these series parallel streams? So actually I have done a lot of research on transducers over sequences and trees, and there are I think some new interesting research opportunities here. And another interesting direction is understanding the complexity of streaming query evaluation. But here we would like to look at parallel complexity, because the parallelism is inherent in the in the structure of the input stream, and we would then like to think about parallel complexity. Query optimization. So for relational structures, there's wonderful work on query optimization. Even for sliding windows, there is a lot of work on query optimization. But now they're richer. These are richer structures where windows could be nested. There could be event-based windows and so on. There could be these temporal joins. So, so we need a good theory for query optimization. And just to get you interested, so the computation that we looked at was first computing revenue, then marking P cars, then computing star taxis and doing temporal join. So in this pipeline of computations, if we switch Q3 and Q2, if I mark star taxis before I mark P cars, then it turns out that the result of the computation stays unchanged, but the marking P cars becomes more memory efficient, because as I explained, to mark P cars, you have to delay the output. So you have to remember the tuples in the subsequent R. And if I've retained only star taxis, if I've done the filtering earlier, then I need to remember less, right? Yeah. So, so how do we do this automatically and in a clean fashion? And finally, I want to mention formal verification, because actually that's my core area of research. And in distributed systems, there is a lot of research these days on verified distributed systems, for example, with verified consensus protocols or verified fault tolerance. If you look at these distributed stream processing, there is very little work in terms of rigorous testing and verification and these kinds of ideas. And I think this synchronization schemas can provide a good basis, because when you want to verify something, if you want to formalize it in a theorem prover, you first need a very solid mathematical foundation on the objects that you are manipulating, right? In the near term, we have started looking at tools for testing and debugging, and recently we have this paper called DiffStream, which is a differential output testing for Flink, where we are trying to find ordering related bugs where the desired ordering is specified using these synchronization schemas. So to wrap up, what I talked about is a new foundation for computing with data streams, where synchronization schemas are types, series parallel streams are objects of this type, and these SPS transformers are transformations, graph transformations over these streams, right? And the benefit would be to bring this world of time series dependent computation into this world of SQL with maybe windowing constructs and so on, and allowing more complex queries with nesting because everything has the same type, right? Has a formal semantics with deterministic behavior where so yeah, streamability is what I mean by that is like this monotonicity in the input stream with guarantees of safe and flexible parallelization. And there are many opportunities for both theoretical and practical research. So thank you. So let me stop here and we can now switch to more questions.
Thank you very much, Rajev, for this very nice talk. And as Rajev said, we have plenty of time for questions if there are on site or on Zoom. Please go ahead. I mean, maybe I may ask a questions before others stand up. Rajev, you mentioned that the design of the concrete query language is still work in progress. I mean, the query languages are definitely one of the core topics in the PODS community, and we are always interested in this trade-off between expressive power and complexity. Yeah. So where in this how to say, in this field between expressive power and complexity is your query language going to be situated?
That's a great question, and honestly, I don't know the answer. So in fact, what we have here are just examples of queries. So for some of these, you know, we know the complexity, but as you said, it's a trade-off, right? Between expressiveness and complexity. But then for expressiveness, you need a yardstick. So in relational query languages, you have, you know, there is a clear yardstick rooted in logic and, you know, relational algebra and so on. And so here it's not so clear because, you know, it's not, so for example, for sequences, you know, if you're just interested, if you forget about data, and if you're interested in regularity, you could say monadic second order logic is your yardstick for expressiveness. So here it's a mix of sequences and relations. And then there is this key-based partitioning, which has at least some form of data. So so it's not clear how what's the baseline for expressiveness. Like when will we say that, you know, the query language that we have is expressive enough? And that's, I think it's it's really an avenue for future research. And that was like one of my motivations for giving this talk at PODS, that, you know, some of the folks here would get tempted to look at this question, right? Yeah. So maybe one could simplify these structures. You could say that, okay, I'm not looking at a particular feature and then understand it, right? Yeah, like bags and strings and binary trees we know, but then if you mix this unbound, you know, the key-based partitioning, then what happens, right? Yeah. So that would be a starting point. And then there is this concern about what queries people really want to write, right? So like the sliding windows and then, you know, complex forms of relational aggregations and these temporal joins, they are all very useful queries. And at best, so currently we can specify them, and what we can do is give precise bounds on how much, what is the complexity of evaluation. But we don't have really crisp theoretical results.
Do you allow me a follow-up question, namely regarding your approach to designing the ultimate query language? Are you following a bottom-up approach that you say, okay, from the use cases we have investigated, we need this and that and those features? Or are you going to apply a top-down approach that you say, well, this is the, how to say, the set of conceivable query features that one might ever use, and from that we will then define restricted languages which are easier to evaluate. So is it rather bottom up or rather top down that you're proceeding here?
Yeah, we are proceeding bottom up. Yeah, we are looking at the queries. Yeah, so I have a student who is trying to implement this and defining some queries, but it's bottom up, saying that, okay, this is a pattern that seems common in practice, and then what's the clean way of specifying it, and what can be ensured in terms of its evaluation complexity, right? Yeah. Okay. But I think top down would be nice. Yeah, if we have some more understanding. Yeah.
Okay, thank you very much. We have a question on site, please.
Hello. Hey, thank you, Rajiv. This is a very nice talk. And I have a question regarding to optimization. One of the trends in streaming today is using materialization to speed up for the querying the result sets. And I would like to know how this SPS-based model, how do you plan to enhance the materialization in this framework? Thank you.
Yes, yeah, thanks for the question. So, yeah, actually, I'm not really an expert on, a database query evaluation. So I don't know the, the latest trend that you specified, but it should be compatible, I guess. I mean, so what we, plausibly, one could do it in two stages. So one is actually this query rewriting, right? Which is what I'm showing on this slide, that, this is motivated by more traditional query optimization for relational queries, that, if you rearrange joins and filters and things like that, then, if you know some statistics of the data, then you can show that, this rewritten version is going to be evaluated more efficiently. And this is also possible here if you say that if I know that, approximately how many GPS events I get between end of R events and how many write completed events I get between end of R events. So if I have some statistics or relative statistics of that, one is say twice as much as the others expected, then we can do a query rewriting proving correctness such that we expect the evaluation complexity to be less in the rewritten form, right? And on top of that, and once you have this more optimized version of the query, then I think you can give it to the other techniques that you were mentioning, like looking at materialized views, or if it's a sliding window type of protocol, then how to do the incremental computation as events drop off and events. So these two are kind of orthogonal, right? Yeah. So the current schemes are more lower level, I think, because they're not being applied to these high level queries, because the high level queries are of restricted form.
Okay, thank you.
Are there any further questions from the audience on site? I mean, Rajev, you mentioned this idea of a yardstick in case of a query language, but here, I mean, in terms of a stream processing system, is there also such a thing as a yardstick that you would compare your model, or not just model, also implementations with? I mean, you mentioned one paper where you compared your implementation with Flink and with Spark. And also I remember in one of the first slides of your talk, you had a whole list of of systems from the Hadoop ecosystem. So where will your system, if it's fully developed and implemented, where will it fit into this landscape?
Oh, that's a very good question. So I think these systems are highly engineered, and it's impossible for an academic team to compete with them in terms of performance. So I think what we are hoping is that we can show that the queries that you can express in our language are more, it's more programmable or more expressive, and you do get guarantees that the parallelization that will happen is going to be safe. It's going, the result of the computation would be deterministic. But in terms of actually building a system that will have performance that's comparable, I mean, there are queries that they can express and we can also express. And on those queries, it would be impossible to show better performance. And so I think the hope is that we can influence some of these commercial systems, and but the whole stack needs to be re-engineered a bit to allow this formalization, though. So I don't have a crisp answer to your question, but I interpret it as, what's the path to technology transition, or can you influence this? And that seems kind of hard, right? And I think the support, it's very clearly, our framework is supports more modular and high-level specifications of queries. But on the other hand, in those systems, you can always write, the user can write their own code. So you can't say that ours is more expressive, because the query that I described here, right? So so this was our query. So I think in all of these systems, it would be challenging to express this query. At some place, you would have either the user has to write their own code, or they have to forego parallelization, or they have to, not worry about correctness and hope that parallelization actually produces the correct result. But it's, if the user wants to write, I mean, you can always write low-level C code, right? And you can program it yourself. And all of these systems allow you to do that. Yeah. But what we have demonstrated is that the natural specification of this query would be four-stage stream transformation. Actually, it can even be broken up into substages if you want. And each concept actually matches well with the the queries that we provide. Like there is sequential aggregation, there is a relational aggregation, there is a temporal time series based marking of ours, there is a relational marking of taxis, and there are temporal joins, and all of these produce objects of the same type, and the parallelization opportunities are exposed at every stage. So for example, to compute the fare, that can be parallelized using standard techniques. Computing the distance for different taxis can be parallelized. Computing the distance traveled by the same taxi should not be parallelized. Otherwise, you would get incorrect result, right? Yeah. So it's more like a programming discipline, and it's a challenge to convince people to adopt kind of a different programming style. But
is it fair to say that your proposal is more towards a declarative style programming than current systems, or would you disagree?
Yeah, definitely. It's more declarative, and in the current system, only the relational operations are declarative, and then the rest you program it yourself. So I mean, I think they all build on top of SQL, but then a lot of these windowing constructs, I mean, there are some fixed patterns provided, and there's some fixed patterns for key-based partitioning, but all those operators cannot be mixed freely. because the concepts are like different at different levels. You have a different structure, whereas here we have only one. The view of data is this series parallel stream at every level. So everything is a transformation over series parallel streams. So you get this composability.
Okay, thank you. Any other questions? Yes, please. There's a question on site.
Yes. Following the previous questions about the query language and the expressivity, I'm also interested in this side. So I think SPS query language is nice and elegant, but in practice or in industry, there are many new languages appeared, and then people keeps coming back to Circle. So Circle still dominates the industry application. So I'm thinking, is that possible that you can actually translate Circle directly to your SPS language instead of like a new language to the application?
No, that's a good question and good suggestion. The offhand, I don't know the precise answer. I mean, it should be possible. So but yeah, I mean, I think your high-level point is well taken, that we could have a language where there are like different front ends where, if you say that, this is my favorite language, then, you should still be able to use it. And then, so this could be actually a lower layer where there could be some additional operators. But if we can show that, this circle can be mapped to this, then that would be a benefit, right? So we have looked at the streaming, the streaming SQL. Yeah, we have looked at it, not in every not every operator, but most of the operators we have succeeded. But the complete, the entire language and the complete proof is still work in progress. Yeah.
Yep, thank you. So a follow-up question is, how do you see the expressive power between Circle and your language?
Yeah, so as I was answering to Reinhard, I mean, this is, in terms of high-level operators, this is more expressive. So for example, these time series dependent computations, they are kind of very hard to express in SQL. But in SQL, you can actually embed C code, right? So it's complete. I mean, it's Turing complete. So any computation can be expressed in SQL. So what you lose is the optimization ability. So I think, so if you embed some user-defined code, then, the optimization doesn't work. And what we are hoping here is that the more higher level constructs here allow you more optimization. So if you just use filters and maps and joins and some forms of windowing and some relational aggregations, then then you should be able to express it at a very high level in SQL, and then it will be well optimized, right? Yeah. But then if you add these temporal joins, or if you add these time series dependent computations, and then some things cannot be partitioned on keys, then you lose the, you can still write the corresponding code there by writing your own functions, but you would lose automatic parallelization and optimization.
Yeah. Okay.
But,
so I have
but we could map. We could provide these high-level primitives and map it to our framework, and then there will be more optimization. Yeah. So that's possible.
Yeah. Yeah. Sure. So I think maybe we can extend the optimization to your language as well. So another question is about the formal verification part. Can you share some unique challenges of applying formal methods in distributed stream processing? This is the first question. The second one is about when we use informal verification in industry, we always face the question is that verification is more done on the abstraction level, which is on the models. How do we extend the guarantees on the models to the code? Thank you.
Yeah, no, again, a great question. So the well, first of all, so let me answer your latter question first. That, you know, what about formal verification of code or real systems? So, so you are right that, you know, in the early days of formal verification, we focused more on proving properties and correctness of protocols at the level of models. But the current trend is actually looking at real systems, right? So like Paxos, or, you know, there are efforts underway to build a verified web browser. So these are not trying to verify an existing system, but try to build a verified system, right? Particularly these core infrastructure, like, you know, web browser, or like Amazon Web Services has this big project on security policies and so on. So there you are trying to build the entire stack in-house in a very principled way, using modern verification tools, like trying to formalize everything in, say, Coq or something like some theorem prover like that. This is very labor intensive, but there are aspects where people are willing to pay this price, and there are, like, you know, verified kernels of operating systems and compilers and so on. And in the context of distributed systems, like fault tolerance protocols and some consensus-based protocols, right? Yeah. So I'm thinking along those lines. So this is more long-term. It's not going to happen in the next few years, that we will have more and more verified components of the system infrastructure. And in the context of stream processing, so what we can build on are the techniques that have been used to build provably correct fault tolerant systems, right? To handle things like replication and fault tolerance correctly, right? So that's a generic distributed system problem, and there are, you know, efforts like that at, say, Microsoft Research and so on in that line. So there is this Everest project. But in the context of stream processing, I think the one interesting aspect is this ordering. So I think that's where this synchronization schemas could help. So the data is arriving at different nodes in the distributed system, and does it have to be ordered or not, right? And if it has to be ordered, then there are these synchronization protocols, which which are more traditional distributed systems components, and we can build on those. But for stream processing, we could say, well, for this query or for this class of queries, we don't need to synchronize those, right? And that's where I think there are new opportunities, and this synchronization schemas work could provide a theoretical basis for doing that. So that's kind of special for stream processing. I think these are relatively, the actual computation is relatively simple, because it's expressed in these high-level languages like extensions of SQL. So there is also that opportunity.
Okay, thank you. Thank you for a good question.
Yeah, but this tool that's mentioned on this slide, diffstream, so this is actually trying to find ordering bugs in Flink programs. And we looked at actually, the way people do debugging of these stream processing programs on Flink's mailing list. And there is very little support for even testing. So I think this is an opportunity for formal methods in programming languages, and generally database theory also researchers. Yeah. The whole distributed stream processing world is focused on performance, right? And in all systems, people first focus on performance, but then later they start worrying about correctness and finding bugs and good infrastructure for finding logical errors in what code they write.
Okay, thank you.
Any further questions? Okay. Okay, then I would like to thank the audience for attending, and above all, Rajev, thank you very much for being with us. It's already close to midnight your time, so I think you've really deserved the rest, because in about 10 hours time you will be with us again. So thank you very much, Rajev, and I look forward to seeing you again in about 10 hours then. Yeah. Thanks a lot.
Yeah, thank you everyone for listening to the talk and for all the questions. Yeah. And yeah, see you, Reinhard, in 10 hours. Yeah.
Okay, bye-bye.
Bye.
Good night, Rajev.